Exponential functions are really easy to graph, particularly if we make a table of inputs and outputs. And we'll use these tables to create graphs and then talk about some of the attributes of exponential graphs. So if I plug in 0, anything raised to the 0 power is 1. Negative powers are going to create fractions. And so let's start by taking a look at 2 to the x power. So we have 0, 1, we have 1, 2, we have 2, 4. So 2 to the x looks something like that, and there's a horizontal asymptote along the x-axis at y equals 0. And hopefully you can see from the table of values that if I increasingly plug in negative numbers, I will never get a negative answer because negative exponents create fractions. They don't create negative numbers. So you're never going to get below 0. If take a look at 4 to the x power, what I want to do in this example is sort of contrast the difference between those graphs. What's the difference between 2 to the x and 4 to the x? Well, not a whole lot. Really, it's just the speed at which this graph is increasing. There's still a horizontal asymptote, but this graph is just going up faster because the base is now 4. Now let's contrast that with the idea of a fraction base. 1/2 to the x power. So what we're getting now when we plug in a negative exponent, we're just going to get a reciprocal. And so what does 1/2 to the x power look like? Looks something like this. And still we have this horizontal asymptote at y equals 0. What happens when we change the fraction to, say, 1/3? We're going to get 3, we're going to get 1/9, and we're going to get 9. So once again, we see this situation where the graph is just going up faster because the denominator has a bigger number. So attributes of the exponential. The y-intercept is going to be 0, 1. There isn't going to be an x-intercept because there's a horizontal asymptote on the x-axis at y equals 0. And the direction will be twofold. As x goes to infinity, if y goes to infinity, we call that growth. As x goes to infinity, if y goes to 0, we call that decay. And then we're talking about the idea of limits again. So, quick sketch. This is growth. As x goes to infinity, y goes to infinity. Decay. As x goes to infinity, y goes to the horizontal asymptote of 0. That's the idea of a limit. So what about graph shifting? So if we know the attributes of the parent graph, we know that this is going to be an upshift plus 1. And what that means is that everything, including the asymptote, moves up 1, including the y-intercept. And if this is growth, it's going to look something like that. So the y-intercept is increased by 1. Everything got pulled up 1. The horizontal asymptote, instead of y equals 0, is now y equals 1. So using graph shifting. Let's take a look at this one. This is a right shift. Well, what that means is that the asymptote is still at y equals 0. Because if I take an infinite line that's going left and right and move it to the right, nothing really happens. And so what I'm going to do here is I'm going to draw a kind of a rough sketch of what 2 to the x would look like. And what's happening is everything's going to get moved over 2 places. So instead of the point 0, 1, we should have the point 2, 1. We're moving over to the right 2 places. Now what that does is it creates this sort of awkward y-intercept. Not really sure exactly. Because when we move the y-intercept up 1 place, I knew exactly where it was. It used to be at 0, 1, and now it's at 0, 2. But we can clearly see that the y-intercept has changed. It's not 1 anymore, but it's not an exact one-to-one relationship. So what we need to do here is just simply find f of 0. Plug in 0 for x. Let's do the -2, and that makes 1/4. So that must be 0, 1/4. So we have to do a little algebra to figure out the y-intercept. Now, as my transformations get a little more complicated, perhaps I want to create a table of values that makes the adjustments for me. So, of course, we've got a downshift here. And this would technically be a horizontal reflection, but what it's actually doing is, because that's a -1 power, it's actually making a 1/3 to the x power, and you can see that in my table of values here. So I could just start by making a table of values for 1/3 to the x power, and then I could just simply take 2 from all the y values. So we're going to get -1 here, we're going to get -1 and 2/3, we're going to get 1, we're going to get -1 and 8/9, and we're going to get 7 there. Now the other thing I want to draw your attention to is the idea of a downshift. Think about what that's going to do to our graph, particularly the y-intercept and the horizontal asymptote. Let's sketch a graph first, and let's see if we can see what's happening. So we have 0, -1, we have 1, -1 and 2/3, we have -1, 1, and we have -2, 7, just about out of room there. So this is looking like this, and hopefully you can see that the horizontal asymptote is in fact pulled down 2 places to y equals -2, and in fact the y-intercept is pulled down 2 places to 0, -1. So hopefully that makes sense based on the parent graph. And hopefully it makes sense on the values that we're getting from our table. Notice that I'm never going to get past -2. I got -1 and 2/3. I got -1 and 8/9. I'm never going to get past y equals -2, hence the asymptote. Let's take a look at another equation. So let's identify, we've got a left shift there, we have a vertical stretch here, and then we have a vertical reflection here. And let's see if those all manifest themselves in the graph. So once again, I'm starting out with typical inputs, and I can get all the outputs for 2 to the x. And then we're going to subtract 1 from all the x values to recognize the left shift, 0, -2, 1, and -3. And then we're going to take all the y values and multiply them by -3. Some of these values, of course, will not fit onto our graph. And let's see if we can figure out where the y-intercept went and where the horizontal asymptote went. So we've got -1, -3, we have 0, -6. So right away I've got my y-intercept there, -2, -1.5, and -3, and -3/4. So hopefully we can see that the horizontal asymptote is still at y equals 0. The y-intercept is at 0, -6. And let's see if we can figure out why the horizontal asymptote did not change. Why did the y-intercept change but not the horizontal asymptote? Well, the horizontal asymptote didn't change because I don't have any up or down transformations. There's no up or down shifts. I shifted to the left, I stretched, and I reflected, but none of that is an up and down shift. So the y-intercept changed because of the reflection and because of the stretch, and that should make sense. But the horizontal asymptote does not change because I didn't shift up or down. Okay, so for our last piece, let's talk about E, which is approximately equal to 2.718. And the graph of E, because E is approximately 2.7, that's equivalent to graphing y equals 2 to the x or y equals 3 to the x. And we saw in our first example that 2 to the x and 4 to the x and 3 to the x, they don't really look all that different. So let's do some inputs and outputs here. So a 0 power is just going to give us 1. Power of 1 is just going to give us 2.7. And negative 1 is going to give us 1 over 2.7, which is approximately 0.4. And that's all we really need to know. We know what the shape of these exponentials look like now. So we're still going to get a y-intercept of 1. We're still going to get this horizontal asymptote at y equals 0. And so getting something that looks like this. And you can see, hopefully, that again, it doesn't look much different than y equals 2 to the x or y equals 3 to the x. And it isn't. So let's take a look at one where we do some transformations. So we've got a horizontal shrink. We've got vertical reflection. And we've got up 3. And you could just as easily write that as y equals negative 2e. Oh, I forgot about the vertical stretch. Vertical stretch. Y equals negative 2e to the 2x plus 3. You can put the plus 3 on the back end to kind of show the up 3. So, starting out with our typical values, 0 makes 1, 1 makes about 2.7, and negative 1 makes approximately 0.4. We can then do all the transformations. We're dividing all the x's by 2 because it's a horizontal shrink. Everything's the opposite when we deal with x, so that's still 0, that's a half, and that's negative a half. And then for y, we're going to do basically 3 things because we have the negative, we have the 2, and we have the up 3. So we're going to multiply by negative 2 and then add 3. So this is actually just going to stay 1. This will become negative 5.4 plus 3, so that'll be negative 2.4. And then this will become negative 0.8 plus 3, which will become 2.2. So let's see what happened to the horizontal asymptote and the y-intercept. So some quick graphing here. So we've got 0, 1, we've got 1 half, negative 2.4, and we've got negative a half, 2.2. So here's what's happening. Because of that stretch, hopefully you can recognize that y equals 3 comes from the up 3. That's the only vertical shift that is here. So y equals 3 is our horizontal asymptote. This is very stretched out. So our y-intercept actually stayed as 0, 1. That's kind of just a coincidence because of all this arithmetic that happened here. It moved and then it kind of moved back to its original position at 0, 1. All right, and the last thing we want to take a look at in this podcast is using the properties of exponents. When you multiply, you add exponents. When you divide, you subtract exponents. The idea of a negative exponent, a power to a power, and so on and so forth. Let's do just a couple quick examples of that. So here's an example where I could rewrite 81 as 3 to the 4th power. And if I write 81 as 3 to the 4th, then, because I have the same base, all I have to do is solve this simple equation, x plus 1 equals 4, and therefore x is 3. Very simple solution. Let's make it a little harder, where we deal with some e's. So e to the negative x squared equals e to the 2x, so a power to a power. That says multiply. And let's bring that up so that all the e's are on the same playing field here. This is going to be e to the 2x minus 3 because you add exponents when you multiply like bases. And once we have that, now we can say, well, I don't really care about the e's. All I care about is that equation there. Negative x squared equals 2x minus 3, which becomes 0 equals x squared plus 2x minus 3, which of course is factorable. And that'll factor into x plus 3, x minus 1. Therefore, x equals negative 3 or positive 1. Those are the values for x. And finally, 2 to the 5x times 2 to the 2x squared. So what I did was I took 4 and I just wrote it as 2 squared. And I'm going to do the same thing with 8. I'm going to write that as 2 cubed. And because I have the same base, I can use the exponent rules that says if I multiply like bases, I get the sum of the exponents. And hopefully you can see the same things happening, that same pattern. Once I get like bases, I can set up a simple equation. I'll subtract 3 to get that equal to 0, and then I will factor it. 2x and x, 3 positive minus 1. Therefore, x is equal to positive 1/2 and negative 3.